All right, this is part 2 of the 4 things to know about the gradient. At the end of the last video, I asked what would be the directional derivative of this function at the point P in the direction negative 3i plus j, and I suggested that we were going to use linear approximation to try and figure out what happens to the value of the function as I move in the direction of this vector. Okay, I've put up here as a reminder that the directional derivative has a formal definition in the book which you need to know and which we're going to talk about in just a bit. But informally, we can think of the directional derivative as the rise in the value of the function over the run, that is, the amount of travel that we do parallel to the xy plane. Okay? Now, for partial derivatives like f sub x and f sub y, the run is always in the x direction or in the y direction. But for directional derivatives, the run can be in some combination of the x and y directions, or even in the z direction if we're working with a function of 3 variables, which we're not here, but will happen later. Okay, so let's say we go along the vector negative 3i plus j, and we want to know what the rise over the run is as a way of trying to figure out what the directional derivative might be. All right, if I want to know what the rise is in the value of f, then I'm trying to calculate a change in f. And I know from section 14.3, that is local linearization, that the change in f is approximately, I should put approximately here because we don't know it's exact. In fact, usually it's not. It's the partial with respect to x times delta x plus partial with respect to y times delta y, where both of those partials are evaluated at the point P, which is 1, negative 2 in this case. Okay, so for us, what that means is this is going to be equal to partial with respect to x, which can be gotten from this gradient here. We calculated it earlier. The partial with respect to x is 2, times the change in x, which is negative 3, because I'm traveling minus 3 units in the x direction. My partial with respect to y can also be gotten from the gradient. It is negative 4. And then my change in y is the amount of travel I do in the y direction, which is plus 1. So my change in f is going to be 2 times negative 3 plus negative 4 times 1. Now let's have a look at the run. That is the amount of travel I do in parallel to the xy plane. Well, the travel that I'm doing is along the vector negative 3i plus j, so I can figure out exactly how far I've gone. The amount of travel I've done is equal to, so this is my rise, and now my run is going to be the magnitude of this vector, which is square root of negative 3 squared plus 1 squared, which is square root of 10. So if I want the rise over the run, that's going to be, and I'm going to replace these with the appropriate numbers or expressions because I want to see the structure of how this works. So my rise was 2 times negative 3 plus negative 4 times 1, and my run was square root of 10. Now, there is another way of looking at that is a little more illuminating. So I'm going to get rid of all this information. I'm sorry I have to erase so much. I wish I had a bigger place to work, but this is my studio for now. Another way to see this is as 2 times negative 3 over root 10 plus negative 4 times 1 over root 10. Sorry about the smallness of my writing there. But again, that's 2 times negative 3 over root 10 plus negative 4 times 1 over root 10. Again, that's 2 times negative 3 over root 10 plus negative 4 times 1 over root 10. Again, that is 2 times negative 3 over root 10 plus negative 4 times 1 over root 10. Where did those numbers come from? These red numbers came from the gradient because the gradient was what was telling me my partial derivatives in the x and y directions. The green numbers are a little bit more mysterious because I never wrote down any root 10s when I was writing down vectors earlier. However, I started with the direction vector negative 3i plus j. And to find the run, I had to find the magnitude of this vector, which was root 10. By dividing by that magnitude, what am I doing to this vector? I'm turning it into a unit vector. So my unit direction vector, which is what we usually call u, is negative 3 over root 10 plus 1 over root 10. Sorry, I'm missing my vector, my components here. I, j. Sorry about that. My unit direction vector is negative 3 over root 10 I plus 1 over root 10 j. Now look at this expression again. And the places the numbers in that expression came from, and you'll realize that the directional derivative, at least my estimate for it based on traveling the entire vector and using linearization, is equal to the gradient the directional derivative is equal to the gradient of f at p dotted with this vector here, dotted with u. And you'll remember the directional derivative we usually call f sub u at p. That's where the dot product comes from, and that's why the gradient is relevant to finding directional derivatives. But note that this was not a rigorous proof, because really I just went in the direction of this vector, negative 3i plus j, and I assumed that the local linearization would hold up, which it really doesn't over such a large distance. And I used that as a guide to finding the directional derivative. And it turns out you actually do get the correct directional derivative, because the only information I used was information about the linearization at that point, which is where the directional derivative comes from. I didn't use any actual information about what happens to this function at the endpoint of that vector. So this does turn out to be the correct directional derivative, but the next thing I want to do is show a correct derivation, a mathematically correct derivation of this formula using the limit definition of directional derivative, and that'll be the third video in this series. But we're coming up on the second point that we need to know about the gradient, which is that it helps us find directional derivatives. So stay tuned.